सर नमस्ते।
हाँ विवास नमस्कार।
कैसे हैं सर?
बढ़िया बढ़िया, आप बताइए क्या?
मैं सर आशीर्वाद है आपका। इंद्र कुमार स्टार्ट कर लेते हैं।
हाँ हाँ, आई थिंक कैन स्टार्ट।
Good afternoon to everyone present here. A very warm welcome to all of you once again to the second session of day 4 of our faculty development program. It is an honor to introduce Professor Surya Prakash Sir, professor in the Department of Computer Science and Engineering at Indian Institute of Technology, Indore. Sir holds a PhD from Indian Institute of Technology, Kanpur, and MS from Indian Institute of Technology, Madras, and BTech from University Institute of Engineering and Technology, Kanpur. His research interests include image processing, computer vision, machine learning, deep learning, and biometric security. Sir has made significant contributions to research with numerous publications in reputed referred journals and international conferences. He has also co-authored 2 books and received the Sir Veseshwaraya Young Faculty Development Fellowship in 2019. Is actively involved in academic and research communities, serving as a reviewer for several international journals and as a member of advisory board, organizing committees, and technical program committees for numerous national and international conferences. Sir also organized several special sessions in reputed international conferences and has conducted short-term courses in area of computer vision, machine learning, and biometric security. We are honored to have Professor Surya Prakash Sir with us today and look forward to learning from his vast knowledge and experience in the field. I would like to call Professor Surya Prakash Sir for this session. Sir, we can start, sir?
हाँ या सर प्लीज अनम्यूट योरसेल्फ सर।
Yeah, because I hope I am audible now.
यस सर।
Okay, good. Good afternoon, everyone. Abhishek, thank you so much for giving this nice introduction. So in this session, as you must be aware of that, we are going to discuss deep learning technique for 3D data. So we are going to proceed in this session this way. So first we will be talking about some introductory stuff. And then after that we'll see what are the different 3D tasks that we do when we are talking about 3D deep learning. And then towards the end, we will be talking about one particular algorithm or one particular model or network, you can say, deep neural network, which is actually used for 3D for the deep learning of 3D data. So before we proceed, let us just have some background of it. So and even before that, let me just make this clear to you that what is the meaning of 3D data, and with respect to that, we will also can understand what is 2D data. So here you see the examples of both. On the left side, you see some samples which are displaying the 2D images, and that we are going to refer here as 2D data. And on the right side, you see there are some samples which are representing the objects in terms of 3-dimensional data. Right? This we are going to refer as 3D data. So when we are talking about 3D data in this presentation, we are actually going to refer this kind of data. Now, what is the difference between the left and right side? So you see, on the left side, you have the normal images that we capture from our normal cameras. So here also we are representing the 3D object. So one similarity is there, that in both left and right images, we are representing the 3D object only. Right here also we are representing the objects which are in 3D, and on the right side also we are representing the 3D objects only, like face. In both the cases we are representing face here. So face is, you know, our face is a 3D object. So in both the cases, we are representing the 3D object, but here that third dimension is represented, uh, or that is being depicted here using the intensity variation. Now on the left, on the right side, that third dimension or the depth is being represented in actual sense. So on the right side, when we are talking about this data, when you are talking about the 3D data, we are referring to this kind of data where we are representing the complete geometry of the object. From this moving sample, I hope everybody is clear with the idea that this data is not giving you only the depth of the object only in terms of appearance. It is giving you the exact coordinate, right? The coordinates of different points that you have on your object, with its complete information in terms of x, y, and z values. So this is very, very important to understand that we are going to discuss everything here in terms of this kind of data. Right? We are going to refer this data as the point cloud data, because you see the 3D object. I mean, here we are assuming that the on the 3D object there are some points, virtual points we are assuming, and then we are digitizing them. We are finding out the x, y, z coordinates of those points, and then based on that we are getting this model. Now the difference between this model and this model is that in the first case we have just the information of the geometry. We just know I mean, like the xyz values of different points that are lying on the object. In the second one, we have the textual information as well. So you can say both are 3D, but here the information is bit rich, because not only the geometry but also the textual content is available. So we are going to discuss everything with respect to this kind of data. I hope now whenever I am referring to the 3D data, you will be having this clear idea. So now here we see the first question, that why do we need to represent the data in 3D? Like here I'm saying that the face is being represented in 2D. Now here the face is represented in 3D. So what is the requirement? What is the need of going to 3D? I mean, we see that we have a lot of face recognition system where we are just using the 2D images and then working with that. So what is the requirement of going for the 3D? So here we see that this is a very real genuine question. Now the idea or the reason here is that whatever we are capturing in 2D, it is all I mean, they're all 3D objects, right? All the 2D images that you see here, they are actually capturing the 3D objects, right? They are only represented in terms of 2D using our normal images, but they are actually 3D images, or they are actually the 3D objects. So if we have provision of, or we are capable of representing these 3D objects truly in 3D sense, and then obviously we will have better representation of the object. And also if we are using, let's say, that data for face recognition, then we'll have better accuracy. So I mean, if you go back here and then see, let's say we are doing the face recognition using this face, or we are doing the face recognition with this face, where we have the third dimension, the depth also available. So then obviously we can expect better results in the case of this, where we have 3D data, right? So one of the reasons we are going for the 3D is this, that objects are in 2D, our objects are 3D, and if we can represent them truly in 3D sense, then the information representation is going to be rich, and that will help us in getting better accuracy in different tasks. Another reason we are going for the 3D is some inherent issues that we have in 2D images. For example, you see here, when we are capturing the 2D images, we see these images are affected by sometimes very high contrast, as you see in this image. Sometimes the contrast might be very low, like where you are not able to differentiate between the foreground object and the background. Then you have sometimes images poorly illuminated. Some part is properly illuminated, some part is not properly illuminated. So all these issues are actually with the 2D images. Whenever we are capturing the images with the help of our normal cameras, we encounter all these cases, right? These problems with the 2D images. Similarly, there's another very big problem with the 2D images, that it is it is very difficult to handle the rotation or the pose changes when we have 2D data. For example, if you have, let's say, a face recognition system where you have trained your system with the help of this image, and if you are, let us say, trying to recognize that person using these, let's say, extreme views, then it will be very difficult to perform the recognition, because in this frontal pose you have different data available, and in these side poses you have different appearance of the face. So this problem and also the other problems that we discussed, like the inherent problems in the 2D images, it can be actually easily handled if we have the 3D data. So as we know, in case of 3D data, we said that the data is going to be represented like this. So here you have the complete geometry of the, let's say, face. So if whether you want the frontal part or you want the side part, you can very easily generate that. So if this kind of data is available, then pose changes can be handled very easily, as you can see. And also this data is invariant to lighting and shadows up to quite extent. It's not that completely it is invariant. It is insensitive, but up to quite extent, it is insensitive to these imaging problems like lighting and shadows. So that is why this contrast issues and then the illumination problems, all these problems will not be there when we are representing our data in the form of either this point cloud or in the point cloud plus texture. So in 3D, our representation is going to be, in a very simple sense, we can say that it is going to be in terms of the collection of X, Y, Z points, and to represent the object, to represent a particular given object, you may have several such points, and then collectively that might be representing the object. So first, we are going for the 3D data representation because it is insensitive to lighting and shadows, and it provides us the complete geometric information. And also, as I just mentioned, that pose variations can be handled very easily if you have the data represented in this form. So because of these advantages, our always objective is to make use of 3D data and then do the recognition with the help of that. Okay. Sometimes we also have the option of, let's say, using 2D data and its corresponding 3D data together. As you see here, on the left side you see the 2D pose of the face, and on the right side you see the same image represented in terms of 3D. So if such combination is available, then that's another advantage. We can even actually use the combination of these two. We can have a multimodal kind of system where we use this also, 2D also and 3D also, and then we can have the further improvement in the accuracy. So we can have, if the correlated 2D and 3D data is available, then that can be even better, and then can serve a good input for different applications. So here we see some applications where we really make use of 3D data. So one of the application is obviously the biometrics that I just showed you, where we are doing the face recognition or maybe other ear recognition also with the help of 3D data. And here we have some additional applications, for example, robotics or augmented reality in autonomous driving, in medical image processing. These are some of the domains where we encounter 3D data. I just want to make a little difference between what you have in case of medical image processing and what you have in these three other cases. These are three other applications here. So in the case of medical image processing, also we represent the object in 3D. So when we are talking about MRI or CT scan images, you have scans, series of scans, and then collectively they represent the three-dimensional object. But in these applications, in these first three applications, we are actually talking about only the exterior geometry of the object. But in case of medical image processing, as you know, when we are looking at the slices or the slices of the MRI or CT scan images, we also see what is inside the object. Right? We are also interested in finding out the interior details of the object. So in the case of medical image processing, you have the volume being represented in terms of 3D, but in other three examples that you see here, only the surface is being represented. So that is a difference. Otherwise, in both, in all these cases, you have the 3D data. So just make this difference, little difference that we have between the 3D data that we have in case of medical image processing and the 3D data in other applications. Okay, so these are the different tasks that we can perform with the help of 3D data. I mean, like object classification can be done, object recognition, as I just said, biometric recognition can be done with the help of 3D data. Object part segmentation can be done. For example, you have a complete 3D object of the, 3D data of some object, and then you want to segregate its parts. That can be also can be done, and then we can also do the semantic scene parsing with the help of 3D data. These two applications, when I show you the data, you'll understand what exactly I'm talking about. But I hope this first two must be clear to all of you. So now we see that currently we see a lot of work happening where the 3D data is being used for. Was not the case earlier, and the main reason was the lack of 3D data. So if we talk about, let's say, 10, 15 years back, we had only very limited 3D objects. For example, in the 2010, if you see any paper, you'll find that all of those papers, when they were talking about the 3D object, they were just using these two objects, like either this Utah teapot or the Stanford bunny. So there was no data available. But at the same time, if you see during that time, for the 2D images, there were a lot of publicly data sets available. So because of that, we did not find much work in 3D domain during that time. But now you see there are so many ways we can have the 3D data available. For example, there are some online repositories where you can go and then download the 3D objects. There are some cloud sourcing platform, for example, the one mentioned here. Through them, you can get the 3D data, and also there are cheap hardware even available which can be used for collecting the 3D data. For example, this Kinect sensor, I am sure many of you must be aware of this. This can be used for collecting the 3D data, and it's quite cheap. So because of all these advantages, now we have good amount of 3D data available, and because of that, we see that a lot of work is happening where people are using 3D data for different applications, right? So if you see 2015 onwards, you will start noticing this work in the 3D domain. And so first thing is that people started working using 3D data because the data was available, and second, which is actually the reason for the 3D data to be available there, is the demand. So you see that there's a huge industry demand in different applications like robotics, autonomous driving, virtual or augmented reality, smart manufacturing. There are many areas where there is a demand of working with the 3D data. That is why, obviously, the publicly data sets were created, and then people started working in this domain. All right. So up to this point, we have covered the first part of our session. We were just talking about the introductory stuff related to 2D and 3D data. I hope you have got the background about this, and then with that, let us move forward and then discuss what are the different 3D tasks that we can perform with the help of 3D data. And if you have any question from this first section, please let me know. Otherwise, we can move forward. If you have any question, you can raise hand or you can unmute yourself and then tell me. Good. So I hope all of you are in sync. Let us move forward. So now we are going to discuss what are the different 3D tasks that we have. So all the tasks that we do, actually we can classify in these three categories. For example, 3D geometric analysis, 3D synthesis, and 3D assisted image analysis. These three categories can actually include all that we do with the help of 3D data. So let us see a few examples in these categories, and then you will understand what exactly I'm saying. So when we are talking about the 3D geometric analysis, here we are talking about analyzing the geometry and then performing different tasks based on that analysis. So we have the 3D data, and that is providing us the complete geometry of the object. So we can just make use of that and then perform. We can analyze that data. We can analyze the geometry, and then perform different tasks. For example, classification, object classification, simple object classification, where different objects are represented in 3D, and then we just want to we want to just find out what is that particular object there, right? I mean, it's like simple classification as we do in 2D with the 2D images. Here we are going to doing with 3D images. So this is one of the application which falls under 3D geometry analysis. Similarly, now next is the object parsing or the part segmentation, where you have the 3D objects, and within the object you want to segment, or you want to classify different parts of it. For example, you want to say that this is hand, or this is the body of the bag. Similarly, in the cap, let's say you want to segregate the different portions of the cap and so on. So when you are going to do this, when you want to do this part segmentation, there also you need to analyze the geometry of the object by analyzing the 3D data given, and then based on that need to perform these tasks. Sometimes you want to like relate the two given objects. For example, one 3D object is here, another 3D object is here. So with the help of geometric analysis, by analyzing the individual or local points on these models or on these objects, we want to relate the two objects. So that can be also performed with the help of 3D geometry analysis. So these kind of tasks that we see here, they fall under the umbrella of 3D geometry analysis. Now we have the next section where we are talking about a 3D synthesis, right? This is the second category in the list that I said. First, we have covered the 3D geometry analysis. Then now we are talking about the 3D synthesis, where we, as the name suggests, we are synthesizing the data. So here we are talking about generating the 3D data. For example, in the first case here, with the help of 2D images, we are trying to generate the 3D data. In the second case, we have, let's say, some 3D data available, but some parts are missing. So we are trying to complete those parts. This falls under shape completion. So this is also a kind of 3D synthesis. And sometimes when the 3D model is available, and with the help of that, we make the shape of the, we do this surface fitting, and then we do shape modeling. So in all these cases, basically, we are generating the 3D data. We are synthesizing the 3D data, and that is why they fall under 3D synthesis. So these kind of tasks are falling under 3D synthesis. And then the last one we have is referred as 3D assisted image analysis. So here basically we are actually analyzing the 2D images only, but we are taking the help of the 3D data. For example, we are doing, let's say, the object, image based. We are performing the image based search. So our query images are the 2D. We are searching the, in the 2D images only. But when we are comparing the 2D objects, two objects which are represented in 2D, we are actually taking the help of the 3D representation of the objects to have the better performance. So in summary, in case of 3D analysis, 3D geometry analysis, the first category, our input is 3D. Like we are doing the 3D, object classification. The object is represented in 3D, and output we can say in 2D. For example, we recognize that the object is chair. So here we are displaying the image of the chair, that the 3D object that is applied to the chair, and that we can show as an output by just using the 2D image of the chair. So in the first category, you can say that the input is 3D and output is 2D. In case of 3D synthesis, you can say in many cases we are talking about 2D images, and then from there we are getting the 3D data. In some cases, maybe this is from 3D to 3D as well, because, like, for example, if you are doing the shape completion, so here we have 3D, and then on that we are adding the missing parts, and then again generating the data. So 3D to 3D. But in most of the time when we are doing the 3D synthesis, where we are generating the 3D data, this is based on the 2D images. We collect the 2D images, and then from that we generate the 3D data. In that sense, we are saying that here, in the case of 3D synthesis, input is 2D and output is 3D. And in case of 3D assisted image analysis, as you see, input is 2D, output is also 3D. So 2D. So for example, you are doing content-based image retrieval, where input is 2D image, let's say 2D image of the chair, and the output is also in terms of the 2D image. But in between, when you are searching, when you are comparing your model, when your query image with the other images available in the database, you are making use of 3D data, 3D representation. It's 3D representation in some sense, so that you can refine your results. So here, 3D representation is assisting us in performing the task. So that is why we are calling this as 3D assisted image analysis. So anything that we do, I mean, most of the things actually are going to fall under these two categories. Either we are going to generate the 3D data, or we are going to make use of the 3D data for different applications. So generation is going to come here, and then many different applications are going to fall under the first category, and very few where we are actually making use of 3D for analyzing the 2D images will fall under the third category. So these are the different tasks that we do. And if you just look at closely, in the case of 3D geometry analysis and in the 3D synthesis, in terms of input or in terms of output, we deal with the 3D. In the third category, in the third case here, we have both input and output in 2D. 3D is only maybe you can say in the background, only for assisting the process. Okay, so up till this point, we have covered the background of this problem, and then some of the tasks that we have, I mean, that are performed using 3D data. Now we are going to come to the main part of this session, where we are going to actually talk about a deep learning algorithm where we are going to use the 3D data. So here, we are going to first see what are the different ways we are going to represent the 3D data, and then we will see a particular algorithm, a particular network called PointNet, which can be used for performing the 3D data analysis. Okay, so let us first see what are the different 3D, what are the different ways of representing the 3D data. Right? Some samples I showed you at the beginning, but let us revisit them again, and also few more other representations. So now, just to compare those representations from the representation that we have in 2D, we can say one thing, that in case of 2D images, our representation is very unique. Like, I mean, all of you must be aware of this, that whenever you have a 2D image, how do we represent that image in computer? Simply in the form of this matrix. If it is a grayscale image, we are going to use a I mean 2D matrix of size n cross n or n cross m, you can say. And if it is a color image, then again just we are going to have another third dimension to represent the channels. And any image in 2D is going to be represented in the form of this kind of unique representation, where we are going to use a matrix, a 2D array or 3D array, you can say, for representing the image in computer, right? And this is, I think, very much known fact, so all of you must be aware of this. But important thing is that in case of 2D, we have this unique representation. You might be thinking that, let's say, in case of RGB, I mean, in case of the color image, we have different representations like RGB or YCBCR, right? Or maybe HSV. Right? There are some other color formats, but in all those cases, you see, effectively you are representing the three matrices only. Right? For example, in RGB, you have one matrix for R, one matrix for G, one matrix for B. So similarly, in YCBCR, also one matrix for Y, one matrix for CV, one matrix for CR. So collectively, if you say this is represented using a three-dimensional array, this is also represented using a three-dimensional array, this is also represented using three-dimensional array. So all these are actually represented with the help of this unique three-dimensional matrix. Okay. Now, when you compare this representation from the 3D, you will understand that what is actually the meaning of uniqueness here. So in case of 3D representation, there are many ways we can actually represent the data, and we are going to discuss them one by one here. So towards the very beginning, when the 3D cameras were not available, which are giving us the point cloud data, during that time, actually to have the feel of the 3D, have the feel of the 3D objects, we used to represent the object by taking multi-view RGB images. So what is the meaning of saying multi-view RGB images? Normally, when you capture any object, you just take one picture from one side, right? You just take one pose of it. But in case of multi-view representation, not only one picture is taken, but you are taking several pictures. So, for example, this is the object. So from all around you go and then just capture the object. So to represent the object, you may be having, let's say, 10, 15, 20 2D images. So though they are not 3D, they are only 2D images, simple 2D images. But since you have you have taken multiple images from all around, we can say that it gives some sense of the three-dimensional representation of the object, and that is why we are putting this under 3D representation. So this is the very basic representation of the 3D objects by using 2D images, where we are in place of just storing one view of the object, we are storing multiple views of it. But truly, if you see, these are the 2D images only. 2D images, but multiple 2D images giving us the feel of 3D. Then the next is the point cloud representation. This representation we saw at the beginning in that example, in that rotating model. So in the case of point cloud representation, you can virtually assume that on the surface of the object you have points, certain points, and with the coordinate frame, every point has been given a coordinate value, and then collectively all the coordinates represent the object. So here you have collection of points. Let's say on the surface of the object, let's say you consider 10,000 points, right? Uniformly, let's say, distributed all over the object. So for all those 10,000 points, you are going to generate all this XYZ value. So you are going to have the point cloud of 10,000 points, and that collectively going to represent the object. So this is a true 3D representation, and this is called point cloud representation. And in our case, the model that we are going to talk about is actually going to use point cloud data for the analysis. Then next is, so up till this point, we have talked about two representations of the 3D objects. One, by collecting multiple objects. Second, where we are, first one is by collecting multiple views of the object, and second is by digitizing, by considering points on the surface of the object, and then digitizing them with the help of their coordinate values. Now, next is, you can say, generated from the point cloud, where we are not talking about just the collection of the points, but also the association of the points. For example, here you see you have points, but the points are also linked with each other. So here we are linking the points, and then we are creating the polygonal mesh. So for example, on the surface you have these points. So earlier these points were segregated, but in the case of mesh representation, we find out the neighboring points and then join them, and then make a surface like this, and then represent the object in the form of mesh, right? So this is called the mesh representation. So here you see you have the points here, and now for every point you find out the, let's say, two neighboring nearest points, and then with the help of that you create a triangle, and you, based on that, you create a mesh. So this gives us the third representation, for the third way of representing the 2D objects. Now this can be further extended, where we represent the object in terms of its volume. So this particular representation is very similar to what we have in case of 2D images. For example, if you have to represent, let's say, the 2D image, let's say this is the area, that scene that you want to represent. What we do. So this is this. We have captured the image for that. So now this image is basically composed of very small units called pixels, right? And when you are storing the image in the computer, what you are actually storing, the gray value or the color information for these small areas. Right? So this big area is divided into these small areas, which are pixels. So you can say your image is nothing but the collection of these small areas, which are pixels. So image is the collection of pixels. When you are storing this image in the computer, you are basically storing the information about these pixels. So exactly in the same way, in case of 3D object, you don't have this 2D area or this kind of 2D plane. You have a 3D object, right? So for example, you have the object represented in 3 dimensions like this. So here what we are doing, we are actually dividing this whole volume in terms of a small unit size cube, you can say. For example, here this 2D area is divided by using, let's say, unit size pixel. So similarly, in the case of 3D, we are going to have, like here, let's say this pixel is represented like this, right? It's a unit size pixel. This is the smallest unit of your image. So similarly, in the 3D, you consider that you have a 3D variant of it in terms of volume. It's a very small cube, let's say you see. So with the help of this small cube, you can divide your whole 3D object, 3D area or 3D volume. And then when you do that, you will find that some of the objects, for example, I mean, this is the object that you want to. And then you divide the volume of the cuboid by considering this unit size cube. So you'll find that some of the unit size cube will fall on the object, some of them will not fall on the object. So wherever the cube is falling on the object, you are showing that here, and those cubes which are not falling there, falling in the object, or which are not part of the object, you are just not showing them. It's something like when you are representing a object here, wherever the object is present, you put the intensity value there, and where the object is not present, let's say you put 0 there, showing that that is the background. So in the same way, here you see that all these small cubes that you see here, they are falling on the object, and that is why they are appearing here. And here also you can say that the cubes are there, but they are not being shown here because they are not part of the object. So this way, given the object, we can represent its volume by using this small size unit volume, and that gives us the volumetric representation of the 3D data. So once we have the polygonal mesh, we can create the volume, and then we can divide that to get the volumetric representation. So this is that has given us the fourth way. Now we are talking about the next way of representing the object in 3D, and this is based on the depth image. So what we do in case of depth image, we have the 3D representation of the data here, where we have all these three values for every point. Now in case of depth image representation, we change this third value to intensity. So for example, here you have a pixel. So for the same pixel here, you at that particular location, at that particular xy, whatever you have the third value, that you change to intensity and then represent that here. So this becomes a 2D image basically. It's really 2D image where the third value, depth value, is now the intensity. So this also can be used for representing the 3D objects. And last we have where we are talking about the primitive based CAD models, where this assumes that any surface that you have can be considered collection of some primitive shapes, right? For example, primitive shapes like the one which you can define mathematically. For example, in a very simple way, you can say plane or sphere or paraboloid and so on, or using B-spline surfaces. So the object is first decomposed into these primitive shapes, and then we get the the CAD model for those primitive shapes, and then collectively with the help of those models we represent the object. So these are different ways of representing the 3D data. Now I hope you get this point that in case of 2D images, we have just simple one representation of the object in terms of 2D or 3D matrix. But in the case of 3D, we have a lot of in case of 3D, we have a lot of ways of representing the 3D data. And if you just analyze these different representations, some of them we can say are regular as our 2D image representation. So in case of 2D image, we are saying that our representation is regular. Why we are saying that our representation is regular in case of 2D images? Because when we are representing any image, every row you will have same number of columns, right? It is going to be always a perfect rectangular kind of area. So first row is having, let's say, the 10 columns, right? Like if you divide it like this, then if the first row is having 10 columns, the second row is also going to have 10 columns, third row is also going to have 10 columns. So that way, it's a very regular representation. So if by considering if you analyze the 3D representation, then we find that we can call multi-view representation as a regular representation, right? Because in multi-view representation, we are essentially collecting the 2D images only and then putting them together to represent the object, right? So these are just 2D images. So whatever property the 2D images have, we have them here because these are not actually 3D; they are 2D images only. Then we have depth image, right? Just now I show you this one. So this image where we are converting the third value to the intensity and get the 2D image, this also is a regular representation. This also gives us a regular representation because we are talking about 3D, but essentially the representation in terms of 2D image. So in first case and the second case, we have 2D representation, and that is why inherently that is regular. In case of volumetric representation, as I just explained, in case of volumetric representation, you are assuming that the object is enclosed inside a cuboid, and then you divide that cuboid into small unit volumes, and then based on that you represent the object. So there also the representation is regular, right? There also here when you're representing the object like this, here also the object representation is regular. Maybe you can say that, for example, for this object, you can say that a cuboid of size, let's say 100 cross 120 cross maybe 50 is required. So in this cuboid, some of the these small cubes will have their presence here, and some of them will be switched off because they are not part of the object. And yeah, I think I didn't mention. So like this 2D, this small unit in the 2D image is called pixel. Similarly, this small unit, this small volume in this 3D representation is called voxel. So this voxel-based representation is also regular, right? But if you see these representations, for example, point cloud representation, polygonal mesh representation, or primitive based CAD models, these all are giving us the irregular form of representing the 3D objects. For example, in the case of point cloud, I'm going to show you an example. In the case of point cloud, this is going to be just a simple text file where you are going to have just all the points listed there. So in some object you might be having 10,000 points. In other object maybe you might be having 15,000 points. So the variations will happen. The order in which the points are being written in the file, that will vary. So that is why we are saying that these representations are not regular representations. Okay, so if you just see the different techniques that are available in the domain of 3D, they can be actually easily classified based on what kind of input it considers for its working. For example, you have some images, some techniques which are using multi-view representation of the object, right? As you see, chair is there, and from all the sides you have collected the data of the chair, and then it is being used for let's say doing certain tasks. So since here 2D multi-view representation of the object is used, you can put the technique in this category. So there are some techniques like you see here where volumetric representation of the object is used. So you can put them here. Similarly, there are some techniques which are based on point cloud, some are there based on mesh, some are based on parts assembly. So the whole literature can be easily classified into these smaller groups depending upon what kind of input the technique is considering for the 3D object, what kind of representation the technique is considering for 3D object. Now, one thing we see here that for the 2D images, we have only single, unique, very regular representation in the form of, 2D or 3D matrices. But on the other side, for the 3D, we have these so many ways of representing the objects, right? Multi-view, volumetric, point cloud, mesh, parts assembly, and so on. So these many different ways are there to represent the object. Now, one question comes in mind when we are talking about 3D deep learning. I mean, as I mentioned at the beginning, we are going to talk about 3D, deep learning model for the 3D data here. So when we are going to talk about the use, we talk about the development of 3D model of or model for deep learning model for the 3D data. The very common question comes in mind that can we extend our 2D models for the 3D data? For example, CNN is a very popular model which we use for the 2D images. So can we extend our CNN model for the 3D data? Okay. So to understand whether you can extend that model for the 3D data or not, we need to understand what is the requirement of CNN. So in CNN, let's say when you're supplying, let's talk about the CNN used in 2D images. So when you're supplying 2D images to the to CNN, what CNN does, it performs the convolutions. So if this is the image given, how is the convolution performed? Convolution uses a filter. Let's say it's a 3x3 filter. So 3x3 filter is going to be convolved throughout the image, and then based on that, whatever response is generated, based on that, the further processing is going to be done. So in case of CNN, the convolution is the basic operation that we perform on the image. So for this, what is the requirement? Our requirement is that the image should be represented in the form of a grid like this, because filter is in the form of a grid, and then when you're going to convolve your image with the help of this filter, then image representation should be in the form of this kind of a regular representation in the form of this 2D or 2D array, or maybe you can say 3D array. So in case of 2D data, in case of 3D data, wherever we have this kind of regular representation, we can say that directly we can extend the extend our 2D models to 3D. So for example, here we see multi-view representation, or the depth image based representation, or the volumetric representation. In all these three cases, we I just explained that you have a very regular representation. In the first two categories, it is these images are 2D only. I'm again repeating it. So I mean, there's no question of being irregular, because I mean, you are just representing the 3D in terms of the 2D images. But in case of volumetric representation, here also, as I explained, this is just the extension of pixel-based representation to voxel-based representation. So this representation is also regular. So in this case, we can actually we can extend the available CNN for performing the classification, let's say classification task. But if we are talking about these representations, point cloud representation, or the polygonal mesh representation, or primitive CAD model based representation, for these representations which are irregular, these are irregular representation, and here directly extending the CNN will be difficult. I mean, we can have some alternate ways to convert the data from let's say mesh to volumetric representation, and then make use of CNN, but directly CNN cannot be applied to these representations. Now, why are we worried about using the CNN on the on this kind of data? We'll learn that, and maybe briefly again mention here that truly, if you compare these two representations, this one set here and the another set here, you will see that this representation is truly 3D. What you are seeing here is, first of all, in first two cases, actually not 3D. In this case, or in this case, it is not 3D. Let me just clear this so that you can see things. So here in the blue box, all these three techniques that you see, they are actually representing the 3D object, but truly this is not 3D. This is not 3D. Right? This is a representation of the 3D object using the 2D images only. In the case of volumetric representation, only you have true 3D representations, but we see that directly when we are doing the scanning of the object from the camera, we don't directly scan the object in terms of volumetric representation. We primarily scan the object in terms of, let's say, point cloud or the polygonal mesh, and then that need to be converted to this. So since these representations are the two representations of the 3D objects, and they are irregular, where CNN cannot be extended directly, so that is why we are interested in finding out a suitable model, or we are interested in developing suitable model which can be used for processing this kind of irregular data. So with that, we come to the point where we are going to discuss a network which is particularly useful for handling the point cloud data, which is the very basic representation of the data, very basic representation of the 3D object, and because of that, this is going to be very, very helpful. So just a brief review. So why we are interested in 3D data, or why we are interested in developing a 3D, a deep learning model for the 3D data, because we have several applications, as you see here, robot, augmented reality, shape design, and so on. So there are many areas where we need to process the 3D data, and because of that, if we have any deep neural network model which can process the 3D data, that is going to be really helpful. So we have just to summarize, refresh you these different representations for the 3D objects: point cloud, mesh, volumetric representation, and projected view RGB. This is nothing but multi-view representation of the object. So here, these three are the true 3D representations. And when you are capturing the object using the 3D camera, what you actually get at the very beginning is this. When you scan, let's say you have a scanner and you scan the object, what you get is this one, point cloud data. This is the most raw form of the data that you get from the scanner. And then after that, you can do some processing and then convert that to mesh representation. And then further, if you want, you are interested in the volumetric representation, then you can do some processing and then convert that to volumetric representation. So here we see that the point cloud representation is the very basic representation. From the camera, we are directly getting the point cloud. So when we are, when we are dealing with a 3D representation, we want our model to be close to point cloud, right? Our model to we want our model which can directly accept the point cloud representation of the 3D objects and can do different tasks, for example, classification and all that. Why we want the model to be like close to point cloud? Our model should accept the point cloud, because when you are capturing the object, let's say you are using the lidar sensor or Kinect sensor, and you're capturing the 3D 3D data of the object, what you are going to get is the point cloud. So if your model 3D deep learning, deep learning model can directly consume point cloud data, then obviously it is going to be the best, because what you are getting from the sensor is directly being used in the model, right? And there are certain other reasons also because of which we are interested in having a deep learning model for the point cloud, and these are as follows. So for different applications, for different representations, for example, mesh representation or the volumetric representation for the depth representation, if you want to, let's say your data is available in the form of mesh or volumetric representation or the depth map, it is very easy to convert that representation to point cloud representation. Very simple. Going from point cloud to the mesh is a difficult task. Like a lot of processing is required, but coming back from the mesh to point cloud is very simple. You can imagine you have a triangle. If you want to, let's say, from this triangle you want to get the points, you just remove these edges, so you'll get the points. But from the points, if you want to go to a triangle, then if a lot of points are given, you have to find out for a particular given point which are the nearest point, and then based on that you have to connect that. So for that, processing is required. But if you want to convert mesh to the point cloud, it's simple. You just remove the connections, then gets converted to point cloud. Similarly, volumetric data can be also very easily converted to point cloud representation, right? And similarly, depth map can be also very easily converted to point cloud representation. I think this you can easily see. So here in the depth map representation, the third value was made the intensity. So you can directly get the XY value from the pixel coordinate, and then whatever intensity you have, with the help of that you can get the third value. So very easily you can actually convert the depth map to point cloud, similarly mesh to point cloud, and even volumetric representation can be also easily converted to point cloud representation. You can see here, though we are representing the surface, but in point cloud representation we are only interested in the surface part. So what all the voxels you have here, which are representing the surface, for them you just can find out what is the XY, these three coordinate, three values, and then just based on that you can represent the point cloud. So when you have the point cloud representation, or when you have the 3D deep learning model for processing the 3D data which can consume point cloud, that is actually going to be the best thing, and that is why we are interested in that. And we see that this point net that I just mentioned is actually a network which can directly consume the point cloud and give you the classification or other different results, right? So I hope up to this point everybody is clear. If you have any question, I'm just stopping here for a minute. If you have any question, please let me know. You can unmute yourself, I guess, and you can speak.
अभिषेक अनम्यूट कर दो सबको, अगर कोई कुछ पूछना चाहेगा तो पूछ लेगा.
Sir, already done.
सर जनरली लोग चैट बॉक्स में ही लिखते हैं लास्ट तक जो भी उनकी क्वेरी होती है.
Okay, okay. Yeah, not a problem. I think, I mean, if no questions, we can assume that the people are following it.
Yeah.
All right, so let us move forward. So this slide gives you a very brief idea about what was happening when, let's say, the deep learning model was not available, which can directly consume the point cloud. Still, people were working with the point cloud, I mean, 3D data. But what was happening when, let's say, I mean, this is the neural network model, or deep neural network model. Right now, we are talking about a neural network model which can directly consume point cloud data, right? But what was happening? How were we handling this 3D? I'm so sorry, just a minute. Yeah. So if you have a deep neural network, right now we are talking about giving the 3D representation or the point cloud representation to this network. But what was happening when this network was not capable of considering the point cloud data? But then even then when the deep neural network was not capable of considering the point cloud data, still the people were working with the 3D data. So there, what we used to do is this, that we used to extract some features out of the 3D data. Let's say point cloud data is given. From the point cloud data, we extract some features, and then we use those features as input to our neural network, and then make use of that for performing different tasks. So here we list some of the techniques actually that that were doing that were those were working like that. So here we see we were extracting the features from the point cloud data, and these were the handcrafted features. I hope in machine learning, deep learning, when we talk about the difference of the difference deep learning and machine learning, we say in machine learning you have to extract the features. These features are handcrafted. You have to do something to extract the features, and then you have to feed that to your machine learning model. But in case of deep neural network, this feature extraction is inherent. So when we were not having a deep neural network which can directly consume the 3D point cloud data, we were using we were extracting some features from the 3D point cloud data, and they were fulfilled from they were actually supplied as input to different deep neural network models. So and those are listed here, like point feature histogram, fast point feature histogram. All these actually techniques are the techniques where we are using the deep learning, but on our deep learning, or I mean normal neural network on handcrafted features. Okay, and in some cases, like we discussed that voxel-based representation can be, I mean 3D CNN can be actually extended for the voxel-based representation. So if you can, I mean, if you have the point cloud in hand, if you can convert that point cloud to voxel-based representation or voxel representation, then or volumetric representation, then you can actually extend your CNN for that work. So there are some works where the point cloud was first converted to, I mean, voxel-based representation, this volumetric representation, and then the deep learning was being done there. So here we see, I mean, let's say we are doing this where we have the point cloud data, and then we are converting that to volumetric data, and then making use of the deep neural network. Then unnecessarily, we are doing the exercise of converting the point cloud to the volumetric representation, and second, I mean, you know, in the case of point cloud, you have only surface being represented, but in case of the volumetric representation, the volume is being represented. So obviously the volumetric representation is going to be heavy compared to the surface representation, right? This point cloud representation. So unnecessarily, when we are taking this indirect route of handling with the point cloud data, we are unnecessarily making the data voluminous. So just to overcome all this, we want, and these are some examples like 3D CNN, what we were doing in the 3D CNN. Here you are converting your point cloud data to volumetric data, and then converting that to voxel representation, and then using the 3D CNN. In the case of 2D CNN, here you are projecting from your 3D model, you are projecting different views, which are actually represented in the form of 2D images, and then you are using the 2D CNN. Or in some cases, as I mentioned, you are extracting the features, you have handcrafted features, and then you are using, let's say, the fully connected network and supplying these features to the fully connected network for uh, performing different tasks, right? So now we have this question. So can we achieve effective feature learning directly from the point clouds, right? And this is the question that I posed several times before. So can we have the option of directly feeding the point cloud data to our network and then doing the feature learning, right? As we do in case of CNN. In the case of CNN, you directly supply the 2D images and then CNN learns the features from that. So can we do that when we have uh, when we are working in the 3D? Can we have a network which can directly consume the point cloud data? So yes, we have such network. It's called PointNet, and it was proposed sometimes back, but and now we have some advanced models also available for the PointNet. But I'm just talking about this very basic one because I think that's a good model to give you the background of this. So for this question that do we have any model which can directly consume the point cloud data? Do we have any deep learning model that can directly consume point cloud data and work on that? So yes, the answer is yes. And here we have this one such example called PointNet. So PointNet can directly consume the point cloud, and it can perform different tasks like classification, part segmentation, and many different tasks. So now we'll see here what is the problem when you are talking about handling the point cloud data. Why it is so difficult to get a network for handling the point cloud data? Why do we need to? What is the struggle? What is the problem? So that actually problem is in the representation of the data. We said that point cloud representation or the mesh representation, these representations are unstructured representation. They are irregular representation, right? And every network you see that there's some form of regularity is required. Like in CNN, you want the regular form of representation in the form of grids and all. So in case of PointNet, in the case of point cloud data, that is actually the there is a problem. So those problems we are going to discuss here. So before that, let me just summarize that this PointNet is going to do end-to-end learning right from the scattered unordered point cloud data. Our point cloud data is scattered, it is just collection of some points, and then it is also unordered. I'll just show you the example. This basically means when you have, let's say, 1,000 points collected from your object, you put your points in any order in your, let's say, text file. When you are opening that file in the software, it is going to show you the same object. So when you have 1,000 points in 1,000 points representing the object, in whatever order you put, the object is going to be same. So this kind of unorderedness is very difficult, very challenging to handle, and we'll see how the PointNet handles that. So this PointNet, the network that we are going to talk about here, this network is giving us end-to-end learning. That means it can directly take the point cloud. You don't need any conversion, and from the point cloud, it can perform these different tasks like object classification or the object part segmentation or the semantic scene parsing. All these things can be performed by the PointNet directly consuming the point cloud data. There is no conversion required. There's nothing required to be obtained from point cloud data and then that need to be fed to the network. Directly, you can feed the point cloud data to the PointNet, and then it can perform all these different tasks. Okay, so you can say that it's a unified network. Multiple things are performed by the same network. So we are saying that this is a unified network. It can do classification, as you see here. It can do part segmentation for different 3D objects. It can segment its parts, and then once the parts are segmented, it can even tell us the semantics of the things like what is chair, which part is the floor, what is wall, and all that. So all these things can be performed with the help of this network. Now let us talk about the two very basic challenges that we need to handle when we are talking about the point cloud data. So first challenge is coming because of its nature being unordered. The point cloud data is unordered data. That means if you have n points representing your object, you can have n factorial permutations of n factorial orders of putting those points. Still, you will see that the point that collectively those points will be representing the same object. So one problem is coming because of the unorderedness of the data, and second point is coming. Second problem is coming because of the geometric transformation. So when your object is, let us say you are scanning the object and object is put like this, let's say. So obviously, and if this is the coordinate frame, for this particular point, you are going to get a coordinate, some coordinate, let's say, right? Let's say this is 10, 15, right? I mean, just take a 2D simple example. Now, if the same object is rotated, object is same, but when you are scanning, let's say the object is rotated. So, I mean, this object is, let's say, coming something like this, right? So this, after the rotation, this point has come here. So obviously, with this coordinate frame, coordinate system, this point is not going to get 10, 15. It may be, let's say, 20, 5. So object is same, but because of this rotation, because of this geometric transformation, which is mainly the rotation, because of this rotation, you see the same object, same point is represented using different coordinate. So object is same, and same you can think about all the points. I mean, let's say you have 1,000 points here. So all those 1,000 points will have some coordinate value here, and all those 1,000 points will have very different coordinate values when your object is, let's say, rotated. But when you are doing the object recognition, let's say this is a chair. So in both the cases, you want to recognize this object as chair, whether it is in this pose or in this pose. You don't want to say that this is chair, but this is not a chair. So we want to recognize objects in whatever pose they have been fed to, but we see here that the data that is representing that object will be very different in these scenarios. So because of this unordered nature of the point cloud data and because of this geometric transformations, we see handling point cloud directly becomes very difficult. So let us see one by one how is the how are these problems handled by the point cloud, and then we'll understand why point cloud is so powerful and it can directly consume the point cloud data. So first we are going to talk about the unordered input. So in the case in point cloud representation, this representation is orderless. For example, we're talking about the representation of the object using n points, and in general we can say that every point is represented using d dimensions. Normally it is going to be 3. The value of d is going to be 3, where in case of point cloud data you have just 3 values to represent a point. But in general you can say d values, maybe for example, let's say along with those 3 coordinate values, you are also associating some other things like color, texture, and all that. So then the vector may be a bit long. So we can say it is d dimensions. So whether you are representing your object like in this format or in this order, where your points are arranged in this order, or you are arranging your points in this order, you will see that both objects represent the same. Both these representations represent the same object. And what has changed here? So you see this in the file. Let's say this second point here has become the first point when you have changed the order. Similarly, this point was the last point here, but this has become the first point here. So order has got changed. But even though whatever is being represented here is same as what is being represented here, right? So for any given object, actually you can have n factorial permutations to represent that object, and all those n factorial permutations are actually representing the same object. And I think that you can understand more with the help of this example. So here you have an example where the point cloud data file is being shown, right? So you see what you see here is a point cloud data file. What is this? Well, let's say one row here. One row is representing one point in this point cloud. So for that one particular point, you have these 3 coordinate values. For the another point, you have these 3 coordinate values, and so on. So this file 1 contains the coordinate values or the point cloud of this particular object. Right? And I'm just showing some part of it, but I mean, usually you will have, depending on how big is your object and how fine the representation is, you may have, point ranging from 10,000 to 40,000, even 1 lakh also. So in the first file, you see that let us assume that you have 10,000 points here. So in 10,000, those 10,000 points have been arranged in this order, where you just see the first, let's say 17 points. Okay, and then rest of the files are points are hidden here in the file. Now what we do, we take, let's say, this first 10 points from this file and remove them from here and keep them at the very end in the file. So what you will get, this 11th row that you see here, this becomes the first row here. You can see all these from this point onwards, you see those points, right? And where have these points gone? We have just cut them from here in the text file, and then we have put them at the very end. So now we get this file 1 with one order of these points, and we get the file 2 with the changed order of the points. Now let us go to the software which can open this file and then see the object. If you open this object, you will see that this face. When you open this file, again you will see the same face. So in both these cases, you will see that whether you are opening file 1 in the software or you are opening file 2 in the software, it is going to show you the same face. That means when you change the order in the points in the point cloud, the representation does not change. And this is actually a problem, because in case of, here, though we have taken out some part of the object, some part of this representation, and we have put at some other place, still we expect that both representations should be considered same. But actually this is not the case when we are dealing with the 2D data. In the case of 2D data, in case of 2D images, this is not the case. We don't do that. So for example, if you have a 2D image, you have a 2D image, let's say like this, and you say that you cut this part from here, or maybe you take this part and swap with this part. Will we expect that both these representations represent the same image? Very clearly no, right? Because you can assume, let's say this is the 2D image, right? Let's say this is 2D image. Now you partition this into 4 parts like this, right? And then you say swap this with this. Will you get the same face? Will not get, because here you have eye here, and then in the next representation we'll find that the eye will be here. The cheek, this cheek part will go there. So obviously, after swiping some part of the 2D image with the other part, you will not get the same image, and you don't expect those 2 images to be same. But in the case of point cloud representation, your expectation is that whether you are following this order of the points or you are following this order of the points, in both the cases, the model should say that yes, this is, let's say if you're doing the face recognition, and then model should say that yes, this is also person 1, or person, let's say N, and this is also person N. Right? So in both the cases, you expect that the model will treat these 2 different files as same, and then will be able to recognize the object. So this is the challenge. So now let's see how is this problem of unorderedness handled in the point cloud representation in the case of PointNet. So here it's a very beautiful and very simple, you can say, a trick is used. So to understand that, let us first understand what is called a symmetric function. So any function where output of the function does not depend on the order in which you have supplied the input, then that function is called a symmetric function. For example, max. Let's say you want to calculate the maximum of x1, x2, x3, and xn. These n values are there, and you want to calculate the maximum. So in your analysis, let's say you give x1 first, then x2, then xn, or x2 first, then x1. Ultimately, the maximum that you are going to get is going to be same. Right? It is not going to be dependent on in which order you have supplied these points in the function. Whatever order you give to the max function, maximum that it is going to produce is going to be always same. So let's say, for example, you said what is the maximum of 10, 20, 30. So this function is going to, this max function is going to give you the value 30. But if you say what is the maximum of 20, 30, 10, again this will generate the 30 only. So such functions are called symmetric functions. So here max is a symmetric function. Similarly, some function is also a symmetric function. Like if you add, let's say you have these 3 values and you want to add them. So whether you are adding first, you're saying 10 plus 20 plus 30, or you're saying 20 plus 30 plus 10, you're going to get the same value. So you can say the sum is also a symmetric function. So in this case, so I think you must be getting now the idea. Here we see that in the symmetric function, The order in which you are supplying your points, or the order in which you are supplying your input, is immaterial. So to handle this problem of unorderedness, or the problem of having n factorial representations representing the same object, is actually being solved here with the help of symmetric functions. Because as you know, if you have, let's say, a symmetric function f, and you pass your file 1, this symmetric function is going to treat this file 1 exactly in the same way uh, like it is going to do with file 2, right? We talked about file 1 and file 2 here. Now this is file 1, this is file 2. So whether you pass file 1 to the symmetric function or file 2 to the symmetric function, this is going to give you the same output. So if you can have some symmetric function where we pass our data and consider the output of that symmetric function in our processing, we see that this problem of permutation, problem of unorderedness is handled. So we do the same here. We make use of symmetric function to handle this here. So basically, when we are dealing with the data in point net, in this particular network that we are discussing, we do some transformation on the data, and then and these transformations are with the help of this, like for example, one with the help of the symmetric function, and then we use the transformed value in our representation. So as you see here, overall, in totality, how the output is produced in the point net is like this: that you have actual input is in the form of x1, x2, x3, xn. Then you are using some transformation on the x1, x2, x3. You are transforming those values, and on those transformed values, you are performing some operation called g, and then whatever output you are getting, that you are associating with this gamma, and then finally what you are getting is the output. So here, this particular operation that we do on the data items x1, x2, x3, xn, this h function, this is this, and then on that this g is basically going to give you the output, which is going to be invariant to the order. So what actually we are doing, so whatever point we are getting here, x1, x2, x3, this is x1 point, this is x2 point, x3. So for all these, or maybe let us better to call them a p1, p2, p3, because other things we can use for the representing the coordinates. So these points p1, p2, p3 that we have here, for them, p1 is represented using x1, x2, x3 value. P2 is also represented using x1, x2, x3 value. So what we are doing, we are not directly going to consider these points, and you can assume that these points, like you have 1, 2, 3, 4 points being shown here. These 4 points are part of, or they are representing some 3D object, right? These are the point cloud. Like you had a list of points here in this file. Similarly, those points are for 4 points we have the coordinates here. So on these points, first we are performing this operation h, and then whatever you are getting after performing h, these transformed coordinates are then used to this. They are fed to the symmetric function g, and whatever output this g is producing, that is actually used in the classification. So you know, this g function is a symmetric function. So right now, we are saying that you have passed your first point as 1, 2, 3, second point as 1, 1, 1, third point as 2, 3, 2, fourth point is as 2, 3, 4. But if you change the order, and you are getting some output of g is a symmetric function. So this output is going to be, let's say, capital X. So this is going to be same even if you, let's say, change the order of the points. You say 1, 1, 1 is the first point, then 2, 3, 2 is the second point, 1, 2, 3 is the third point, and 2, 3, 4 is the fourth point. Let us say you see that. So since it is again going to pass through this g, and g is a symmetric function where in what order you are supplying your coordinate does not matter. So still output is going to be x. So so I mean, you see that very beautifully this symmetric function is able to handle the permutation problem. Right? So before using the, let's say, data in your network for classification, we are going to pass it through the symmetric function, and symmetric function is going to give you a representation which is invariant to the order, so that way we will be able to handle the permutation problem of the point cloud data. Now, what is this H function? Let me just first tell you. So we can say that why are we first applying some this H function on 1, 2, 3 or these coordinates, and then you are performing this symmetric operation? Why are you not performing the symmetric operation directly on these original coordinates? Right? So this H function basically projects your coordinates to higher dimensional space. Like here, the points are represented in 3 dimensions. This function projects the coordinate in higher dimension. And why the higher dimension projection is required, that we can understand from this synthetic example. So let us say your symmetric function is a max function, and before using your point cloud data, you are passing it through the max function, and then whatever output it is generating, that output you are using in the classification. So let us see what happens if you are using, let's say, the max function on this original data, right? So let's say max function gives you the maximum of the 3 coordinates that you have for these different points. So what will be the maximum of this first column? You see 2. What is going to be the maximum of second column? This is 2, 1, 3, 3. So maximum is going to be 3. Here it is going to be 4. So 2, 3, 4. What we are going to get? Only 1 point out of these 4 points. Now it is very easy to see that what object you are representing, let's say any object that you are representing using these 4 points, if you just want to represent that with the help of this 1 point, you will lose the information, right? These 4 points might be representing that it's a square, or maybe let's say some shape, but with the help of 1 point you can't represent the shape. So a lot of information you are losing if you are actually performing this symmetric operation in the original space. So now let's say we embed it in the higher dimensional space. We project it to the higher dimensional space where, let's say, the space is 12 dimensional space. So here every point is now becoming a 12 dimensional point. So let us say 1, 2, 3 becomes a point like this. 1, 2, 3, first 3 values are 1, 2, 3, and then remaining are zeros. Similarly, 1, 1, 1, when it is projected to the 12 dimensional space, first 3 are 0, then these are 1, 1, 1 here, and then trailing are zeros. And similarly, 2, 3, 2, when it is projected, you get these zeros here and these zeros here, and 2, 3, 2 you get here. Similarly, this point you project in the 3D, so you get 12 values here. I mean, these 8 values as 0, and then last you're getting it 2, 3, 4. So now when you're projecting your data to the higher dimensional space, obviously you will see that you are going to have these values, but along this, all the other dimensions are going to be 0 or near 0. So now, let's say you have projected your data in the 12 dimensional space, and this is the representation. And now you compute the max operation. So you see, when you're computing the max operation for this column, you get 1. When you're computing the max operation for this column, you get 2, and so on. So now, if you analyze this vector that you are getting now, you are getting some representation where the representation of every point is there. For example, this particular part is representing 1, 2, 3. This particular part is representing 1, 1, 1. This particular part is representing 2, 3, 2. Last part is representing 2, 3, 4. So you've not missed anything. Here, when you directly computed the max of these 4 points, you only got 1 point, and in that the information was missing. But here also you got only 1 point, but this 1 point, this one representation is rich in the sense that it has actually the representation from all the points. Right, so when you're projecting your data from low dimensional space to the higher dimensional space, actually we see that in the output of the symmetric operation, you have the representation from all the different points that you had in your original data. Now, one question might be coming in your mind that this is a very synthetic representation where I have represented the object in such a way that we have projected. I'm projecting these vectors in such a way that non-zero part is not overlapping with the other non-zero parts, right? So I've done this just to give you an example here, just to make you understand the concept, but in reality also this is very much true. That means what is very much true? That non-zero part of one point will not overlap with the non-zero part of the other point. And this is true because when we are going to project our data, we are going to project our data in a very high dimensional space. For example, in this particular network, we go from 3-dimensional space to 1, 0 to 4-dimensional space. So originally you have 3 values, and then you are in the higher dimensional space, you are going to have 1024 values representing the same point. So you see that a lot of zeros are going to be here. So when you have when you are projecting your data in the higher dimensional space, and uh, there, I mean, if you see, analyze it, you will find that the data vector becomes very long and a lot of zeros are there. So when you talk about the intersection of non-zero part of the different points, you'll find that there might be some places where two non-zero parts overlap, but in many cases you will find that there's no overlapping and you will be able to retain the information. For example, let us say in this 12-dimensional space, this and this would have overlapped, let us say. So then you will lose this information, but still, if this and this would have not, it has not overlapped, then you would be able to retain the information from these points. So like that, let's say you have 10,000 points in your object, but out of those 10,000 points, for let's say for 2,000 points, you have a situation where this non-zero part is not overlapping. So at least you will be able to retain the information from those 2,000 points, and with the help of that, you can perform the recognition. All right, so that is why this embedding, higher dimensional embedding, this use of H function is required here, so that this low dimensional data becomes high dimensional data, and then when you are taking the use of symmetric function, you don't lose the data, right? So yeah, I think let me just skip this part. So here we see that with the help of this projection, what we get on that, if we apply the max function, then the output of this is going to be quite rich in terms of the representation, and can work very well for I mean, representing the object. And for this H function here, we are using this MLP, which stands for the multi-layer perceptron network. And for the max, we are using max pooling. You can say, I mean, it's a simple max operation. We are just calling it max pooling because this is the common word that we use in case of deep neural network. So, so we have seen up till this point how to handle the n factorial permutation problem of the point cloud data, or unorderedness of the point cloud data. So, and just to summarize, this is handled in point cloud with the help of the symmetric function. Now we'll see how this particular network handles invariance of I mean, how does it achieve invariance with respect to geometric transformation, or how the geometric transformations are handled. So again, it's a very simple approach here. So what it does, so we I mean, at the beginning I was just explaining what is this problem, and there I said, when you have, let's say, the object represented like this in this orientation, and when its orientation becomes different, then since the point cloud representation will be different, you will have a problem. So what it does, this network says that before using this data, first align it to some in standard direction. So don't consider this data as it is, or don't consider this data as it is. First align this data to some standard direction, right? So for example, let's say you consider a axis representing this longer spread of the data here, right? So let's say this is the axis which is representing the high, I mean, the direction in which is the highest variance you have in your data, right? So now let's say you have some provision to bring, and you also calculate the mean of this data. So you bring the center point of this data, mean point of this data to 0, 0. And then if you can align this axis with the x-axis, you will see that this data will get represented something like this. And if you do the same thing for this, you will find that actually exactly same representation you will get here as well. So here also this is the longer axis. So what you do, you compute the mean. So mean is here, bring it to 0, 0, and then you align this axis to x-axis, let's say. So here also you will find that this will get represented like this. So now you see, originally they were different, but after this transformation, you are getting the representation which is exactly similar. So now if you get the XYZ points of this representation or this representation, it is going to be same. So by doing this, these transformations or these alignments, you can say, so before using the data, this network first aligns it to some standard axis and then uses it for classification, let's say. So then because of this, it happens it is able to handle the problem of geometric transformation. So here the idea is to automatically align the object to a standard axis and then make use of that for for different tasks. So for the alignment, you have, we have here a network called TNet. TNet is, we're not going to talk about the details of the TNet, but TNet is actually a network which basically performs the transformation. So with the help of TNet, for the given input, we need to find out what are the transformation parameters, what are the parameters with the help of which this automatic alignment will happen. Once those parameters are then available, then we can apply those parameters and do the transformation on this input data. Right, this is the input data, like we are saying that it is like represented like this. Now with the help of this TNet, we are getting the parameter to align this, to bring this to 0 0 and align this axis to x-axis, let's say. So once those parameters are available, we transform this and get a new representation where now your data is represented here in a unique way. So this TNet gives us the transformation matrix, and you know that when you are what transformation you are going to do here, translation and rotation, right? When you are changing this object representation to this representation, you are only translating the object and rotating it. So we need a 3x3 matrix for that, and TNet will you give the data, TNet will generate this matrix, and once this matrix is available, then it's simple matrix multiplication. You can directly take the matrix, multiply that to this data, and then the data will get transformed to the new to new values. So with the help of this, automatic alignment, this network is able to handle the geometric transformations. And here we see the geometric transformations actually happen at two levels. One on the original data. Here you see where input is of 3 dimensions, and at the intermediate level where the input becomes 64 dimensions. So you see that when I show you the complete pipeline of this network, you will see that this network has this intermediate input at a particular stage, and then again to realign there, we are using the same mechanism. Okay, so yeah, so this is the complete pipeline of the point net model. So you have input given in the form of 3D, point cloud data. So you have n class 3 input matrix, you can say, n points, and all points represented in 3 dimensions. Then first, before using this data, we are going to align it. So for that alignment, we are going to use this transformation network, TNet and matrix multiplication that we just discussed. So on this data, you are applying this transformation, and then you are getting the same data represented in the aligned way. So here n class 3 was the basic input that you got, the input that you got, and then after transformation, the same data, same number of points, same way, represented in the same way, but now they are aligned. Now once this alignment happens, then we are projecting these points to 64 dimensional space. So at the beginning, if you remember, I said that this network projects the points to 1024 dimensional space. So from 3 dimensions, we have to go to 1024 dimensional space, but that doesn't happen in just one go. It is like a 2-level processing. First 3-dimensional data is projected to 64-dimensional data, and then 64-dimensional data is projected to 1024-dimensional space. So that's so the first level of projection is happening here. So you have aligned the data, and then you are doing the projection. Now after this projection, again you need to align it. So alignment on the original data, then projection to 64-dimensional space, then again alignment in that 64-dimensional space. Here we are calling this as a feature transform. Earlier we were calling it as input transform, because that transformation was directly implemented on the input data. Here we are saying that this is a feature transform, because now from 3-dimensional data you have gone up to 64-dimensional space. So we are calling that representation, 64-dimensional representation, as a feature or feature vector. So we are saying that we are doing the feature transformation, but the approach is same. Whatever data we have here, we are now going to align it to the standard axis, and with the help of that we get the unique representation. So now first alignment, then projection, then alignment, and then now again we have the projection to go to the 1024-dimensional space, right? So this is the alignment, then projection to 64-dimensional space, then again alignment, then projection to 1024-dimensional space. So here you see input was of 3 dimensions. Now it has got converted to 1024. Right? number of points are same, n and n. N points are now being represented in the form of 1024 dimensional space. So now, once you have your data is projected, what is the next we need to do? We need to pass it to the symmetric function. So now it is passed to the symmetric function, max pooling. So we get one vector out of these n vectors, and this is going to represent the whole object. So your whole object, which was represented using n points in the 3 dimensions, now is represented in using only one vector in 1024 dimensional space, right? And now this can be fed to this vector can be fed to your, let's say, fully connected network, and then the classification can be done. So here you have, this is like fully connected network, and you're feeding it to that, and then it is doing the classification and telling you what is the class level. It's k. Let's say you have k classes, and then so it is giving you the output for the k classes, right? We can say probabilities for the k classes. Now, we discussed at the beginning that is a point net is a unified network. It can also do the part segmentation. So for the part segmentation, for any object that you're considering, for the part segmentation, you need to you require it's individual parts to be considered, right? Local features to be considered. Here what you are getting is a global feature, right? You had, let's say, a big object here. This whole big object is now represented using just one feature vector of size 1024. So there's no local information here. This global information is available, and with the help of that you can do the classification. But within the object, if let's say you want to classify, or you want to segment that this is one part, this is another part, this is another part. So for that you need local information. So for that, here we are fusing this global feature with the local embedding. What is local embedding? You see, for the same point cloud representation, which was in 3 dimensions, now this is represented in 64 dimensions. So the number of points are same, only you have projected them into higher dimensional space. So whatever representation you had at the beginning for all the details, all the points that you had in your model, so for all those models you have some local for all those models you have the information here. So we can term this representation as this feature representation as the local embedding, because for every local point that you had in your input, we have the representation here in this feature space, right? So now when you combine this local embedding with the global embedding here, it is actually performs the part segmentation. So here, for performing the part segmentation, this network takes this local embedding, which is of size, let's say, 64 dimension, and this 1024 dimensional vector associated with all these local embedding. So this will be total 1088 dimensional vector, like n vectors of dimensions 1088. Now these vectors are actually now used, and they are analyzed to do the part segmentation. Now this is capable of doing the part segmentation because here you see you don't have only the global information of the object available, it also has the local information. So with the help of combination of the local and global information, we actually we do the part segmentation. Okay. Yeah, so now let us see a few results for this. This table actually compares the results of the point net to those models where the 3D data was used, but it was not used directly in the form of point cloud. It was, let's say, converted to 3D representation, like volumetric representation, and then it was used there. So here you see the point net is performing 89.2% accuracy. It is giving 89.2% accuracy in the classification. And this technique 19 also giving you 89.2% accuracy. But even with this 89.2 accuracy, we are happy in the case of point net, because in this case, this accuracy was obtained after converting your point cloud representation to volumetric representation, and then it was fed to deep neural network. And here what you are doing in the case of point net, directly this is point cloud is fed to point net, right, which is a deep neural network. So directly this deep neural network is considering a point cloud. So this conversion is not required. Conversion of point cloud to volumetric representation and then feeding it to the deep neural network. It is not required. So, I mean, you see a lot of computation is saved. So because of that, even though the accuracy is same, but it's still we can be happy because we are getting this accuracy on the point cloud, which is the most raw form, which is the representation that we directly get from the scanner, right? These are some visual results for the part segmentation. So you see in different objects, different parts have been also segmented quite efficiently. These are the numerical results for the part segmentation. So here you see the semantic scene parsing. So you see, I mean, like I said, different for the given input, different uh, parts of the scene have been segmented very properly. For example, the roof has been segmented, the table part or the floor, right, is very well segmented in all these cases. So for example, in all the cases you see blue is representing the roof, right? Tabletop is represented using this color. In all the cases, you are able to detect that this is a tabletop, or this is floor, or this is ceiling, and all that. Okay. Now, I just want to highlight this one point for the for this network, that this is very robust to missing data. Right? So here we see that when we have almost around 50% of the data missing, the accuracy drop is only 2%. What is the meaning of saying that 50% data is missing? So for example, in your one object, you were representing the object using 10,000 points. Now you and I mean, for, I mean, let's say you have some 100 objects. For 100 objects, you had some number of points used for their representation. For example, first object using 10,000 points, maybe second object using 15,000 points, and something like that. So every object is being represented using, let's say, some points, endpoints. Now you remove from those representations, from those files, half of the data. Let's say something was some object was let's say represented using 10,000 points. Now you remove the 5,000 points from there and just see. And you do the same thing with all other objects. So if everywhere in all the objects, you remove the 50% points and then see what is the accuracy, what is the classification accuracy you get. So you see that we see that here that this accuracy, there is a drop in accuracy obviously because a lot of data has been removed, but the drop is very less. For example, only 2% drop it shows when it comes to comparing the results when 100% data was used and when 50% data was used. Okay, so this is quite robust to missing data, outliers, right? For the noisy data, this is all. This network is quite robust to all these situations. And if you compare this to the 3D CNN, where we are, let's say, converting our point cloud data. I mean, I just told you those two scenarios. Point cloud data is get converted to volumetric representation, then it is used in deep neural network, which is just, let's say, 3D CNN, right? And here you have point cloud data that you are directly feeding to PointNet. So in the second scenario, I mean, these two scenarios are being actually compared. So in the first scenario, blue curve, this blue is representing the PointNet, and this one is representing, red one is representing the 3D CNET. Now you see, when you're moving in this axis, the missing data is increasing. Like say 20% data is missing, then 40, 60, 80, and this curve is showing the drop in the performance. So you see that the performance of the CNN is dropping very fast. It is, I mean, when the data is missing from 20 to 40 to 60, you see that the drop is very steep. But in the case of PointNet, it is not that steep, right? I mean, there's some degradation there, some drop is there, but it is very slow compared to what we see in case of 3D CNN. So 3D CNN is not found to be very robust to missing data or the noisy data, but PointNet is very robust to the missing data or handling the noisy data. Okay. Now, what is the reason for it? I think it's very important to understand. What is the reason for this network to be robust compared to missing data. So, I mean, for that, if you recall, we said that in the point net, whatever input you are supplying, that input has endpoints. Now that is going to be represented using this global feature vector, and then this is going to be passed to the fully connected network where you are going to perform the classification. So that means the whole performance that you are getting here is actually dependent on this global feature, this global feature vector. And if you see, out of endpoints in your input data, let's say you had 10,000 points, right? Out of those 10,000 points, how many points are contributing to this global feature vector? So we just discussed that this global feature vector, since we are computing the max pooling on this data, which is projected to 10024 dimensional space. So after performing the computing the max of every column here, you are going to get here this global feature vector, which is also going to be of dimension 1024. So here all these feature vectors are 1024 dimensional vectors. Now, out of all these points, right, you have endpoints, right? On the row you are showing endpoint, first point, the second point, third point, fourth point, fifth point, and so on. Now, out of these endpoints, you are going to get 1024 values here. Now tell me, so you can see that you can visualize that you are getting some value here. Who is contributing to this value? Let us say this particular point. The fourth point is contributing to this value. Like means fourth point had the max value with respect to this column. The fourth point had the maximum value. So that is why that value has come here. Similarly, for let's say for this particular point, who is contributing? Which value is coming here? Let's say this particular point's value is coming here. Similarly, for third point, for third value, who is contributing? Let's say this particular point, right? Similarly, for the fourth point here, who is contributing? Let's say this particular point, and so on. So let us say, I mean, let's say for this particular point here, this particular point is contributing. All right. So we see the point that the value that we are getting here is contributed by 1 point out of your endpoints. So if I ask you this question, how many points are contributing to this feature vector? I think it's very easy to see that there are 1024 points out of endpoints which are going to contribute to this global feature vector, right? Because one portion of this 1024 dimensional vector is going to come from some 1024 points, right? So now we see there are 10,000 points here, but we are saying that this this vector is only obtained by considering 1024 points. So that means all these 10,000 points are not contributing to generation of this vector. So when we are removing the points from this, as long as we are not removing those 1024 points which are contributing to this feature vector, we see that the performance will be intact. It won't get affected, right? Because your performance of the classification is going to depend on the global feature vector, and this global feature vector is unaffected by removal of those points because you are removing those points which are not contributing to 1024 points, these 1024 values, right? So, I mean, we are not selecting and then removing only those points which are not contributing. We are randomly selecting, but since you have 10,000 points, it is highly unlikely that you will remove too many of those points which are contributing to 1024, this 1024 dimensional vector, right? So maybe we can say that out of when you are removing 50% of the points from the, or maybe 20% points of the 10,000 points. So maybe some points will get removed from this 1024 also, but other points will remain there. So they will contribute to the accuracy. So when you are removing points from your original data space, as long as you are not removing too many points from the those points which are contributing to this 1024 dimensional space, your performance is going to remain I mean, like almost similar, right? So that is the reason here. Now those points here are called the critical points. So this is the object shape, and those, I mean, this object has 10,000 points. Now here, I mean, I'm just giving an example. So you have too many points here. Now out of those too many points, here you see that these points are exactly those 1024 points out of these 10,000 or 15,000, whatever number of points you have here. These are those points which are contributing to this, I mean, contributing to the recognition of this object, and that is called the critical point set. So as long as when you are removing the points from this original space, from original representation, as long as you are not removing those points which are making this critical set, your performance is going to remain the same, and that is the reason we get good performance even when we remove the 50% of the data, because when we are removing the 50% of the data, I mean, some points from this set will be also get removed, but not too many. All right. So yeah, I guess this is already done, so I can conclude here. So in summary, what we have seen here, we saw a network called PointNet, which is a deep neural network, and it is capable of consuming directly the point cloud data, and it gives us a unified network. That means it can, the same network, one network can perform many different tasks, for example, classification, part segmentation, and semantic segmentation. And this particular work that I presented here was presented in CVPR in the year 2017. So as you said, some advanced versions of PointNet has also come, like for example, PointNet plus plus is there. So I mean, if you have got interest in this, I mean, for the PointNet, you can go to this website and then get more details, like related paper or and code is also available, so you can get that and then use it. And if you are really interested, you can also explore other advanced versions of the PointNet, and then and if you are working in this domain, you can make use of the 3D, I mean, these networks for handling your 3D data. So with this, I thank your patience, and I stop here. If you have any question, it will be really my pleasure to address them. Thank you.
Thank you, sir. Participants, if you have any question, you can ask, please. Sir, it was nice session, very informative and very knowledgeable.
Thank you. Thank you.
चैट बॉक्स में किसी का क्वेश्चन है?
नो क्वेरी सर। सर कोई क्वेश्चन नहीं।
हाँ ठीक है, I think no problem. So we can assume that everybody has followed. So,
Yeah.
so that's a good sign. So we can conclude.
हाँ सर. हाँ इंद्र.
Thank you so much, Professor Surya Prakash sir, for sharing your deep knowledge and perspective with us. Today your session was highly informative and mind expanding, and it has certainly added immense value for our program. Thank you, sir.
Sir, thank you very much. मतलब it was really very nice, sir. And
Thank you, boss. Thank you very much for calling.
अरे सर, ये तो मतलब मेरा सौभाग्य होता है हमेशा. And one more thing I would like to share with all the participants कि sir is my senior in BTech, so it's my privilege and honor to have you, sir, here. Thank you so much, sir.
Thank you. It was my pleasure as well to be part of this program. Thank you and wish you all the best.
Thank you, sir. Pranam, sir. So participants, that is the end of today's session, and we'll start tomorrow at 10:15. And the last session has been rescheduled. Now it will be started from 1:30 p.m. and it will be followed by the valedictory session that which will be started at 3 p.m. So it is requested to all of you that make sure your presence in that session. And in the meantime, we will share a form where you are requested to write your complete and correct name with your affiliations, so that we can process for the printing of certificates accordingly. One more thing, openly announced as per our norms, if the attendance of any participant is less than 70%, then it's quite difficult for us to provide this participation certificate to him or her. So again, thank you for your valuable time, and a special thanks to Surya Prakash sir for this wonderful session. Thank you, everyone.
Thank you, sir.